If we're done with plane mirrors, we can move on to curved mirrors. Now, under curved mirrors, like I said previously, there are two types of curved mirrors: the convergent and the divergent. How do you get the difference? Looking at it, you realize if I'm to take this curved piece of glass and I want to coat one side, unlike a plain piece of glass, no matter what I coat in this diagram, the effect shall be the same, looking at it from the front or the back. But with this curve right now, there is substantial difference. If I if I coat the outside, then I'm going to have to be looking through the internal surface. But if I was to coat the inside, I will have to be looking through the external surface. And so you realize what I should see should be different because they have different geometries. If I'm looking through this internal surface, any ray of light that comes here gets focused to a particular point. As you can see right now, it sort of bounces them inwards, and therefore this is referred to as a convergent mirror. And another name for this convergent mirror is concave mirror. Now, for this guy on the other hand, it's going to bounce them outwards, as you can see from the geometry. If I was simply to move my diagram this way, if I'm to come here, if I'm to meet this guy like this, based on its shape, my bounce will go that way, reflect me that way, this way, and so as you can see, it's bouncing them outwards or diverging them from their paths. This is referred to as a divergent or a convex mirror, and that's the geometry. Now, however, if you look here, the point where they are, and if you look at the lines, also imagine them to continue. There's a point where they all meet. That point is referred to as the principal focus. However, in this case, my principal focus is outside the mirror. That's for a convergent mirror. While for a divergent mirror, my principal focus happens to occur inside the mirror. Is that okay? So this occurs inside. That's why we use broken lines to demonstrate that here we are analyzing within the mirror, while here they are still bounced outside. So that is outside the mirror. So we use straight lines, and that's the basic difference between the two. One bounces out, one seems to bounce from in. Now, with these two mirrors, however, they have different terms in common, like the one I just mentioned just now, the principal focus. This is defined as the point on the principal axis where all rays of light close and parallel to the said principal axis either converge, as you can see here, or appear to diverge from after reflection. If you notice in the definition, we also measured a term, principal axis. Principal axis is the straight line passing through the center of the mirror. That's the principal axis. And if you also look at this mirror, if you look at this curve, you can also hypothesize that this curve initially must have come from a circle, right? Now, if you look at that idea and it was made from a circle, then the imaginary center of this circle is referred to as the center of curvature. And so we can also have the radius of curvature, which is the radius of the sphere from which we cut out this mirror. Okay, so we look at different terms. We know there's a radius of curvature. There is also a center of curvature. There is a principal focus. And the distance from this center of curvature to the principal focus is referred to as focal length. We shall have to pay special attention to this because in future analysis we shall do a great deal with the focal length. So if I was to put an object in front of this mirror, depending on the position of my object will determine the type or the position of image I shall obtain. Please note, with your divergent mirror, you can always obtain virtual images. Always virtual images. And virtual images are always upright. However, with your convergent mirror, you can obtain both virtual images and real images. But keep in mind that real images are always inverted. That means upside down. So you obtain real images which are inverted, but at times you can also, or in a special occasion, which is when your object happens to lie between the focus and this pole, then you can obtain a virtual and upright image. Now, you can do a little bit of extra study to analyze carefully how the different positions of the image will affect the object which is gotten. But there's a simple way by which to analyze them, which is called the mirror equation, which tells us that no matter what happens to the question, you can always be able to determine the type and position of the image with a very, very simple formula. And that formula is, let's write the heading. This is your mirror equation. And the formula is 1 over u plus 1 over v equals 1 over f. Our u here represents object distance. That is how far the object is from the mirror. Our v represents image distance, which is how far the image is from the mirror. And our f represents the focal length of the mirror. However, when solving, there's a convention we use to ensure accurate answers. The convention is as follows. The principal focus or the focal length of a concave mirror, your convergent mirror, is taken as positive. So that means your concave mirror f is positive because it exists in the real plane, while f is negative for convex mirrors. As you are aware, we have to use broken lines to find that. So in your convex mirrors, the focal length you're solving is taken as negative, while the f is taken as positive for concave mirrors. Now, also, the image reproduced is also an important thing. If your image is real, then v is positive. So v is positive for real images, while v is negative for virtual images. That's what tells us that in my mirror, if this is my mirror, put it on this side, everything formed on this side is positive, while everything formed on this side is negative. Everything outside the mirror, we take them in our convention as positive. If my principal focus forms outside the mirror, then it's positive, while for your convex mirror, the principal focus forms within, it is negative. If my image is formed outside the mirror, it is also positive, while from inside the mirror, it's also what? Negative. Now, one more thing we must know about concave and convex mirrors is that they can actually alter the size of the image. So unlike a plane mirror in which your image and your object are always the same size, in your concave or your convex, which are both your curved mirrors, they must alter the size of the image. And therefore, we have a formula that says magnification, which is how much bigger we made our object, is equals to v over u, or height of image over height of object. Quite simply, this means if your question tells you an image 5 times the object is formed, that means your magnification is 5. An image 1/3 the object is formed means your magnification is 1 over 3, 1/3. It is that simple. And with these formulas, we can solve for questions under your curved mirrors. And as usual, we shall refer to our app. Again, you are seeing usefulness. We shall refer to our app to solve one or two questions. Now, we are starting with a simple one. This one is from 2012, question 30. Where can a man place his face to get an enlarged image when using a concave mirror to shave? A man wants to shave the concave mirror. Where should he place his face to get an enlarged image? Now, the options are between the center of curvature and the principal focus, at the principal focus, between the principal focus and the pole, at the center of curvature. Now, like I told us before, if this is your mirror, depending on your position to this mirror, the same type of image you get. Now, you can simply know this simple part. The closer you get to your mirror, the bigger your image begins to appear. When you are far from the mirror, your image is small. The closer you get, the bigger the image for a concave mirror. So for this man to actually get an enlarged image, this man has to be between the pole and the principal focus. He has to put his face between these. But the conventional shaving mirror is a convex mirror, which is also what is used in your driving. Because when driving your car, you want to be able to see the car behind you. If you replace your car mirror with just a normal plane mirror, then you shall not be able to see the full car. Instead, you will see just outside of the car, which is not very effective while driving. Instead, use a convex mirror, which will actually give you a smaller image, which is why you can look within that mirror and see the full car behind you. And there's also the general warning on the mirror, which you should all know by now. If you do not know, please step outside and take a look. Images in this mirror are closer than they appear to be. You should not be confused. Okay, and with that in mind, we've looked at this, and then you can also solve more examples that have to do with using this formula. So let's take some examples under our mirror equation. And one more time, we are taking these examples from our O3 Schools JAMB app. Now, we're starting with a question from 2010, question 29. It simply states that an object 4 centimeters high. Now, when solving most questions, the best way to start is by noting your parameters. Then in your JAMB, you may not have time to note this all exactly or beautifully, but you must note them. An object 4 centimeters high, which means the height of the object is 4 centimeters, is placed 15 cm from a concave mirror. This object is placed a distance of 15 cm. So the object distance is 15 cm from a concave mirror. Remember how to say it. For concave mirrors, our F is always positive. The focal length is positive. The concave mirror of focal length 5 cm. We have to find the size of the image. Now, if you are asked in any question to find size, that must mean you are going to be referring to magnification. So how do we get there? Remember, 1 over u plus 1 over v equals 1 over f. So 1 over u, which is 15 in this case, plus 1 over v, which we do not know, equals to 1 over 5. Correct items. 1 over v, let's keep that here, equals 1 over 5 minus 1 over 15. The LCM of 5 and 15 is 15. 15 into 5 is 3. 15 to 15 is 1. That means we'll be having 3 minus 1, 2 over 15. And v equals to 15 over 2, which is 7.5 centimeters. So our image distance is 7.5 centimeters. And one more thing to note, because my image distance is positive, that means I'm getting a real image. And from this point, all you have to remember is that magnification is equal to v over u, which is equal to height of image over height of object. So 7.5 over 15 equals to height of image over height of object, which is 4. Simplify over 15 gives you 0.5. That's height of image over 4. Cross multiply, the height of the image will be 0.5 times 4, which is 2 centimeters. And that, as you can see in our app, is option D. Quite easy. Just note your formula and proceed. We have a different question here. This is from 2008, question 32. An object of height 5 centimeters, again, is placed 20 cm, from a concave mirror of focal length 10 cm. And now, this is on that point where we have to highlight to you the importance of our app. As you can see, these are two different questions, but they are basically the same in structure and form, with only difference being in the figures. And that is the use of your past question when studying for JAMB, and that is part of what this app will help you develop. Once you solve questions like this, when you see them occur in your JAMB, it is quite easy to solve them again. And looking through these two, notice that our method is exactly the same. 1 over u plus 1 over v equals 1 over f. That will give us that 1 over 20 plus 1 over v equals to 1 over 10. For it's like terms, 1 over v equals 1 over 10 minus 1 over 20. LCM of 10 and 20 is 20. 20 into 10 is 2. 20 to 20 is 1. And that will be 1 over 20. So v equals to 20 centimeters. And if you look at this question, even without proceeding further, you notice that your image distance equal to the object distance. If image distance and object distance are equal, then image height and object height shall also be equal. So our answer therefore must be 5 centimeters. See? But if you want to proceed nonetheless, height of image over height of object equals to v over u. So height of image over 5 equals to 20 over 20. They both cancel out, so height of image equals 5. See? Very, very simple. Let's try one last example and see how we can proceed if the question comes in a different form. In this example, we are being told a real image. Oh, one more time. The year is 2005, and this is question number 24. A real image. A real image. That means our V must be positive. That's why you have to keep your eye out for those keywords, real or virtual. A real image 3 times the size of the object. And once you are told 3 times, that's your magnification. And magnification is going to be 3. So a real image 3 times the size of the object is formed 24 cm from a converging mirror. That means my image is being formed a distance of 24 cm from the mirror. Because we already know it's positive, we don't have to write down the plus, but it is formed 24 cm, which is this. What is the focal length of the mirror? Find focal length. How do we simply do this? First thing, remember, magnification equals to V over U. So 3 equals to my V, which is 24, over U. Cross multiply, 3U equals to 24. So U equals to 24 over 3, which is 8 centimeters. Upon obtaining my object distance and knowing my image distance, then I can find my focal length. See how it goes. So that will give me 1 over our object distance of 8, image distance of 24. So LCM is 24. 24 into 8 is 3. 24 into 24 is 1. So that will be 4 over 24. And you turn both sides up, upside down, or you can simply say 4 here 1, 4 to 24 is 6. and therefore F equals 6 centimeters, which, as you can see again from our app, is simply option A. And you see, this is how we solve our questions. Very, very easy. And notice we get the positive answer. This positive answer here implies that my mirror must be a converging mirror or a concave mirror. As you can see, it's still in the question, a converging mirror. So you can also use that to help you know if you're on the right track. If you were to solve and get a negative answer, when you know your question said you're dealing with a converging mirror, then there must be an error somewhere, and you simply have to find it. And on this note, we've come to the end of our classes on reflection of light. I hope you've enjoyed this class. Alright, so please do well to subscribe to our channel where you can get more videos under this topic and more, all teaching you how to work with our O3 Schools JAMB app. My name is Athanasius. Thank you very much for listening.